Right, and we are back to discuss rational functions. This can be a topic that can be up to 30 marks. So it is a section that I want you to go through and to practice and make sure you understand how to do each component of it. Okay, let's have a look at if you are asked to sketch rational functions, then we kind of go through the following steps. Okay, so the first thing we do is we find all the equations of any asymptotes. Okay, we then find stationary points. If you are still a little bit stuck, you can determine the shape of the graph and classify stationary points as whether they are local, min, or max. Most of the time, you can kind of visualize it and see how it looks. Then your next thing is to find intercepts. Only get your points of inflection if you are actually asked to find them. Okay, if you have no idea how to sketch a particular graph, plot points. Use your calculator, get into calculator table mode, and just plot points. Remember, you can't get marks if you leave something out. All right, so let's go through our asymptotes. So the first thing we've got is our vertical asymptotes, okay, which basically is the nicer one. It's really when your denominator is 0 or you have a limit that does not exist. I like to think of it as if I can't get rid of my denominator, like in this case, x minus 3, then I have a vertical asymptote at x equals 3. If I can get rid of my denominator, like in this bracket of x plus 2, can cancel with the numerator there. And so I have a removable discontinuity at x equals minus 2, which if you remember, that is a hole in the graph. And if I want to work out the coordinates of my x minus 2, if you look at it once I've cancelled that, I can then substitute minus 2 into x's place, and I'd end up with negative 1 over 5. Okay, so yeah, so if there's a removable, it's because you couldn't get rid of that, because you could get rid of the denominator. Okay. All right, horizontal asymptotes. So that is your limit to infinity, as we've discussed earlier. So let's look at the 3 different ways that a rational function could be asked. So if the degree is the same, so in other words, the numerator and the denominator have a degree, the highest degree is exactly the same. So in this particular case, it's x over x. Your horizontal, your limit to infinity, is going to end up being the coefficient of those values. So in other words, it's y equals a half. And you can see why, because when you find the limit to infinity, you're going to divide through by the highest degree, which in this case is x, and you end up with 1 over 2. Okay, because that one's going to be 0. If I look at a bottom-heavy graph, okay, and I divide through by the highest degree, so which is x squared, so I'm going to divide the top and the bottom, every term by x squared, and you can see you're going to end up with 1 over x, which the limit to infinity of 1 over x is 0 over 1. So it's going to be 0. So your horizontal asymptote for any bottom-heavy graph is always going to be y equal to 0. It doesn't matter what the coefficients are. Okay, and then in the other scenario where you have a top-heavy graph, top-heavy meaning the degree in the numerator is higher than the degree in the denominator, okay, you can see that when you find the limit to infinity and you divide through by the highest degree, which is x squared, you're going to end up with 1 plus 0 over 1 over x, which is 0 minus 0. So you're going to end up with 1 over 0, which is undefined, and so there is no asymptote. Okay, so in summary, you are going to get a horizontal asymptote if the degree is equal, top and bottom, or if your fraction is bottom heavy. Okay, and if it's equal, it is always the coefficient of the highest degree, the coefficients of the highest degree, or if it's bottom heavy, it's always y equal to 0. Okay, so what happens if it's top heavy? Well, that's when you get an oblique asymptote. Okay, so remember that there's no way then that you can get an oblique asymptote and a horizontal asymptote at the same time, because the fraction has to be top heavy, the oblique, and the other scenario is a horizontal asymptote when it's either bottom heavy or equal. Okay, all right, so how do we get the oblique asymptote? There are 2 ways. There are still quite a few schools and people that do long division, and that's fine. Okay, and remember when you do long division, it is the quotient that you get at the top there that is your oblique asymptote. Okay, or you can do it by inspection, which I think there are many more people who do this. Okay, so if I am doing it by inspection, I like to write the numerator 2x squared plus 7x minus 4 is equal to the dividend, in other words, what you're dividing by. So then that multiplied by the quotient plus the remainder. So that kind of comes from if you've got 7 over 2 as a fraction, okay, if you look at your numerator, you could write it as what you're dividing by. So dividend, I can't remember if it's dividend or divisor. So you're dividing it by 2, timesing by the quotient of 3 plus your remainder. Okay, and it's your quotient that becomes your oblique asymptote. So if you look at this now, you've got, because this is quadratic and you're dividing by a linear, it's going to be linear times a linear gives me a quadratic and then plus my remainder. And whatever that bracket is, that's going to be my oblique asymptote. And you can seriously do this by inspection, because you can say, when we do it by inspection, we start at the beginning term and we work our way all the way through. Okay, so we can start to say x times what gives me 2x squared. So clearly that's going to be x times 2x. Okay, then the next thing I look at is 7x. Okay, now if I put my inners together, I'm going to get 2x. And then if I put my outers together, I'm going to get another something x. So 2x. So obviously b has to be 5. So that 2x plus 5x must equal to 7. Okay, then I look and I see, all right, to get my remainder, I can say that, well, when I multiply my last and my last together, I get 5. I'm supposed to have minus 4, so to balance it out, I subtract 9. Okay, and then once I've got it in that form, my oblique asymptote is y equals 2x plus 5. Okay, once you've practiced a few of this, it is very easy. You can actually go and do from that step straight into that step straight away. Okay, so give it a go. All right, so let's go back to sketching this graph. Okay, when I'm sketching a graph, a rational function like that, I always find it quite useful to factorize my numerator at the same time. So that, because sometimes you find that it's easier to work with this expression and sometimes it's easier to work with that expression. It depends what you get asked to do. Okay, so what do we know so far? We know that the vertical asymptote is -1. We know the oblique asymptote is 2x plus 5, which means there's no horizontal asymptote. Okay, we then are going to find our stationary points. How do we find our stationary points? We differentiate. I'm going to use that expression rather, so I'm going to use the quotient rule, and then I'm going to make it equal to 0. And when I simplify my numerator, and remember that when you've got a fraction, it's only your numerator that you are interested in when it's equal to 0. And when I plug that into my calculator, or you want to use your quadratic formula, you will see that you get imaginary roots, and so hence there are no turning points. Okay. All right, so now we've got asymptotes, stationary points. Next are my intercepts. Now, when I'm working with my intercepts, it's easier to see it when it's in factorized form, because obviously my x-intercept is when y is 0, so it's basically where my fraction is equal to 0, and that means my numerator has to be 0. So I can see straight away from there that x has to equal to 1/2, or x is equal to -4. I label them as coordinates. Okay, when I want to get my y-intercept, I obviously put 0 into x's place. I always think this is the easier option because you can just remove all the terms that have an x in it. Okay. All right, and I think we are ready to draw it. So when we sketch it, remember to sketch your asymptotes first. I would have put this purple one as a dotted line just to represent that it is actually an asymptote. Label it 2x plus 5. Label your other one, x equals -1. And remember that a graph, so there were no turning points here, where there were x-intercepts, so plot them, label them. And then you will always find that your graph gets pulled towards your asymptotes, always. Okay, all right, so the shape here was quite predictable. Once you had your x-intercepts and you had your vertical and your oblique asymptote, you knew that your graphs got pulled towards them. Right, nice and easy. Okay, in this particular question, you are given the function linear over linear, which actually by this stage you should know that if you get a linear over a linear, you know your graph's going to be a hyperbola. Okay, I've put in all the different possible questions they could ask you. There's no way they'd ask you all 6 of those, maybe 2 of them. Okay, so let's have a look. The first one is find the equations of any asymptotes. So really 2 marks. You can see that you're going to have the vertical asymptote. You can't get rid of that denominator. So your vertical asymptote is x equals 1. You can see that your degree is the same top and the bottom. So I can just look at my coefficients of the x values, and I can see that y is equal to 1. Okay. Right, then my next thing, remember, if there's a horizontal asymptote, there is no oblique asymptote. You don't actually need to write that. That's just to remind you. Right, then we go and we do the coordinates of the intercept. So also nice and easy. When I'm looking at the x-intercept, I only look at the numerator. So I know x is equal to, the x-intercept is minus 3, 0. And when I want to get the y-intercept, I can just block off the x's and I can read 3 over negative 1 is also negative 3. Okay, so I've got my intercepts. What is the next question? Show that there are no turning points. So if I'm going to show that there are no turning points, either, like we had in the question before, we're going to get a quadratic in the numerator that provides us with imaginary roots, or we're going to get a numerator that is a constant. Okay, so if you look here, if I apply the quotient rule, okay, I end up with my x terms cancelling out, and I end up with negative 4 over x minus 1 squared, which clearly cannot equal 0, because the only way that a fraction can equal to 0 is if the numerator is equal to 0. So if the numerator is already equal to negative 4, there's no way it can ever equal to 0. Okay, so hence there are no turning points. The other thing they often might ask is show that the turning point is a decreasing function. So why would this be a decreasing function? Because my gradient is negative, or my derivative is negative, because I'm going to have a negative divided by a positive. Okay. And I think we are now ready to sketch the graph. So when we sketch the graph, remember to label your asymptotes. So you've got x equals 1, you've got y equals 1, and you've got an x-intercept of negative 3, you've got a y-intercept of negative 3. I would actually also label those coordinates, or intercepts rather, and then remember that your graph gets pulled towards your asymptote. So again, it's quite a predictable graph. All right, if I'm then asked to find the absolute value of that graph, what am I going to do? Anything that was under the x-axis gets bounced over. So anything that was under gets bounced above it. Okay, it really has just been reflected over the x-axis, which remember means that the y changes sign. Okay, all right, otherwise everything else remains the same. And if you ever get given an absolute value inequality where it is an inequality with algebra on both sides, it really, how we like you to do it in our syllabus is to sketch both of these functions and then look and see where the one function is above the other. So now I've already sketched this function, okay, and now I'm going to sketch the graph y equals 2x plus 1, which is a nice straight line graph, okay, and I look to see where is the red graph above the green graph. So it is from here. Okay, so obviously in this this graph, I can see perfectly what my x value is, but that's because it was done on a computer package. Okay, you would need to work out what that value is. And so what are you going to do? You're going to solve where 2x plus 1 is equal to my hyperbola, but because this part hadn't been bounced, okay, we didn't bounce it when we found the absolute value, the straight line is equal to the positive version of that. So if this straight line had intercepted this particular graph over here, okay, now this part had been bounced, so then you would have said, okay, hold on, it's going to be 2x plus 1 equal to the negative version of that graph. Right, and then you solve for x, and you will always get 2 possible answers. You look and you see which one makes sense. x equals 2. So remember I asked you where is this graph greater than or equal to that graph, and so my answer is greater than or equal to 2. Don't leave it at that. Just always read the question. Okay, these can be worth up to 8 marks, something like that. All right, then the next one I want to do is, now that we've sketched a few graphs, what I want you to do is I want you to pause the video, okay, and I want you to try and see if you can label or match rather the correct equation to the correct graph. Okay, so go through each of these and decide which is the graph that I would sketch for each of these. Okay, another option is to practice sketching the graphs, is to sketch each of these ones and to check, but obviously you wouldn't do that in an exam, but that is a way of just practicing sketching the graphs. Okay, so pause it. All right, welcome back, and these are your answers, so hopefully you got them correct. Okay, let's go through why they are. So 6.1, I can see that, yes, just by looking at it, I might have a vertical asymptote at x equals -2. But when I factorize the numerator, I'm going to end up with x minus 2, x plus 2. So I'm definitely going to be able to get rid of that denominator. And remember, when you get rid of that denominator, you're going to have a hole in the graph. So you're going to have a removable discontinuity at x equals -2. So I'm looking here, and this is the only one with a hole in the graph. So that is what my graph would look like. So it actually is the graph x minus 2, but a hole in the graph at the point x equals -2. All right, so I hope you got that. The first one is B. If I look at the second one, if I factorize the denominator, I'm going to end up with x minus 3, x plus 2. Okay, so I know I've got two asymptotes at x equals 2 and at x equals -2 and at x equals 3. So I'm now looking at E, and I'm potentially looking at F. Okay, so I've got to look and see what is the difference here, and I can definitely see E has got an x-intercept and F doesn't. So if I go back here, I can see that from 6.2, my numerator, the x-intercept would be x equals 2. So I'm tending towards the graph E. Okay, all right, so then if I look at the third graph, I've got a denominator here that's a perfect square. So if I factorize that, I'd end up with x minus 3 squared, which means that I have one vertical asymptote at x equals 3. So I'm now looking here at D, or I'm looking at C. Okay, all right, so now I've got to think, what else do I know? I definitely know the degree is the same at the top and the bottom, so I have a horizontal asymptote of y equals 1, and so there's my giveaway. There could be also other options that might take you in the direction of C, but that was it for me. So I've got my C, and then obviously process by elimination. The other one is the last one. Oh no, there actually are more than one graph. So let's have a look at this one here. The fourth graph I'm looking at, there's also a vertical asymptote at x equals 3. Okay, well, I'm basically just left with this graph, but at x equals 3. But what, because it's top heavy, I would have an oblique asymptote. And on this computer package, they often don't show the asymptotes. They don't come up, but actually there would be an oblique asymptote that runs right through there. Okay, otherwise you can also, I can see that when I factorize the top, I'd also have a perfect square of x minus 2 squared, which means I have an x-intercept at x equals 2, and it's going to end up turning on that because it's a repeated one. Okay, so I hope that makes sense. In the next video, I'm going to do some more interpretive questions. Okay.